Take a look at this. It is a fortress that has stood against weather and time for more than 800 years. Its walls have watched empires come and go. Now look at this. This is a structure less than 30 years old, a product of what we consider advanced engineering, and it is failing. It is cracking and tearing itself apart from the inside. We are a civilization that can send robots to Mars and edit the code of life itself. Yet we build our homes, bridges and cities with a material that often seems destined to crumble within a single lifetime. Why? What did the builders of these ancient castles understand that we have let ourselves forget? The answer is not some lost recipe or secret ingredient. It is something more fundamental, a completely different philosophy of building. For centuries, our ancestors built not for brute strength, but for resilience. They created structures that could breathe, flex, and in some cases even heal themselves. But here is what most people miss. Before medieval masons mixed their first batch of mortar or laid their first stone, they had already solved the problem that destroys most modern structures. They solved it by understanding what not to do. Section 1. Our modern reliance on rigidity. To understand the thinking of the past, we first have to examine the foundational flaw of the present. And that flaw is built on a material we see everywhere: Portland cement concrete. It is the bedrock of the modern world. It is the silent grey scaffolding for our cities and highways. And there is a reason we embraced it so thoroughly. Coming out of the Industrial Revolution, concrete seemed like a miracle. It is fast, it is predictable, and in compression it is phenomenally strong. We measured its worth in compressive strength and its efficiency in how quickly it could be poured. We built a world in a hurry, and concrete was our go-to material. But in that rush, we overlooked a critical weakness. We became focused on rigidity, believing that the best way to fight the forces of nature, ground settlement, water and time, was to create an unyielding, immovable barrier. We built our world out of a rigid shield. But the problem with a shield that cannot flex is that the moment it takes a hit, it cannot absorb. It shatters. The self-destruct mechanism we built in, the failure process begins almost right away. As new concrete cures, it shrinks, creating microscopic fissures. If the ground shifts or settles, the rigid slab cannot flex, so it cracks. Then water gets in. In colder climates, that water freezes, expands, and acts like a jackhammer, widening the cracks from within. This is the freeze-thaw cycle. But the real self-destruct mechanism is something we put there ourselves. Concrete is strong when you push on it, but weak when you pull it apart. The 19th century solution was to embed a skeleton of steel bars or rebar inside. The concrete handles the compression. The steel handles the tension. For a while, it works. But concrete is porous, like a very dense sponge. Over time, water and oxygen find their way to the steel, and when they do, rust begins. This is not just a cosmetic problem. The corrosion product, the rust, can expand up to 6 times the volume of the original steel. This expansion creates an immense internal pressure that attacks the concrete precisely at its weak point, its tensile strength. The concrete cannot stretch, so it breaks. Chunks spiral off, exposing more rebar, and the cycle accelerates. To top it off, the production of Portland cement is a primary contributor to global carbon dioxide emissions, accounting for up to 8% of the world's total. So we have come to rely on a material that is not only structurally brittle, but also has a brittle relationship with our planet. And while major bridges and buildings are often designed for service lives of 50 or 100 years, many more common concrete elements start showing signs of significant decay far sooner, sometimes in just 15 years. Section 2. The medieval solution, started underground. If our modern approach of rigid sealed construction has such deep flaws, what was the alternative? To find the answer, we have to go back to an era before Portland cement and steel reinforcement. We have to look at the work of the medieval masons. They held a profoundly different philosophy. They did not see their structures as static objects at war with nature. They saw them as systems that needed to work with the forces around them. And their first move, they dug. Secret number 1. Build on the bones of the earth. Before medieval masons laid a single stone, they dug. Not just to level ground, but to reach bedrock itself. When builders began construction on Hereford Castle in England, They excavated down 8 feet, 2.4 meters until they struck solid rock. They leveled that bedrock surface and built directly onto it. No concrete pad, no rebar, just stone on stone, locked together by gravity and centuries of accumulated pressure. This was not random. It was engineered precision. They understood something modern engineers calculate with computers. The strongest foundation is no foundation at all. It is the earth itself. Modern homes. We build on compacted soil. Even with concrete footings, the ground beneath settles over time. Cracks form, walls shift, doors stop closing properly. Medieval castles had no such problem. Their foundations were literally the bones of the earth. Bedrock does not settle. Bedrock does not shift. And 800 years later, these structures stand exactly where they were placed. Secret number 2. The invisible engineering. But reaching bedrock was only half the battle. Medieval engineers understood that water, not invading armies, was the real threat to their fortifications. Before a single wall stone was placed, they engineered elaborate drainage systems. Deep trenches were dug around the foundation perimeter and lined with clay to create waterproof channels. These directed rainwater and groundwater away from the structure, preventing the hydrostatic pressure that destroys modern concrete foundations. Inside these trenches, they placed layers of gravel, what we would call a French drain today, though the technique is at least 700 years older than its name suggests. This gravel layer allowed water to flow freely underneath the structure without ever touching the load-bearing stones. Compare this to a modern home. We pour a concrete slab and hope our sump pump does not fail. Medieval engineers built passive systems that required no power, no pumps, and no maintenance. 8 centuries later, they are still working. The moats we think of as defensive features, they were also overflow drainage systems. When heavy rains came, water flowed into the moat rather than pooling against foundation walls. Stone gutters and downspouts directed roof water away from the structure. Every element worked together as a system designed around one simple principle: keep water away from the foundation. Modern concrete foundations fail primarily because of water infiltration. Medieval foundations never had this problem because the water never reached them. If this engineering from 800 years ago is solving problems that still plague us today, think about what else we've forgotten. This channel exists to uncover these lost techniques and test them against modern methods. We dig through academic papers, archaeological reports, and historical records to bring you practical knowledge that actually works. If you want to see more forgotten technologies like this, hit that like button. It tells YouTube to show these videos to more people who need this information. And if you're enjoying this deep dive into medieval engineering, hit the subscribe button. It genuinely helps the channel grow. Now, let's talk about what medieval masons did with the materials themselves. Section 3. The material philosophy. Once they reached bedrock and engineered their drainage, medieval masons turned to materials. And here is where their philosophy becomes truly radical. Their primary tool was a material that was, by design, soft and forgiving: lime mortar. The intentionally weak link. For millennia, lime mortar was the primary binding agent used across the world. It begins as limestone, which is burned in a kiln to create quicklime. This is then slaked with water into a soft paste called lime putty, and finally mixed with sand. Unlike Portland cement, which hardens quickly through a chemical reaction, lime mortar cures through a gentle process called carbonation. It slowly reabsorbs carbon dioxide from the atmosphere to turn back into limestone. This can take months, even years. In fact, when researchers analyze the core of an exceptionally thick medieval wall, they can sometimes find pockets where the lime, shielded from atmospheric carbon dioxide, has remained relatively soft and uncarbonated even after 800 years. To a modern engineer, that sounds like a defect. To the medieval mason, this was the point. This slowness was a feature, not a bug. It resulted in a material with 2 key properties: breathability and flexibility. First, breathability. Lime mortar is vapor permeable. It is like a technical jacket for a stone wall. It allows moisture vapor to pass through and escape, preventing water from getting trapped inside, the primary cause of frost damage and decay. Modern cement mortar, in contrast, is significantly denser and less vapor permeable. When used to repair old stone buildings, it can act like a non-breathable barrier, trapping moisture inside the wall and causing the historic stones themselves to decay. Second, and more importantly, Flexibility. Lime mortar is intentionally softer than the stones it holds together. This seems counterintuitive. Why use a weaker glue? Because its job is not to create one giant rigid block. Its job is to be a sacrificial cushion. When a medieval wall settles or expands with temperature changes, the soft lime mortar absorbs the movement. It might develop tiny cracks, but these stay in the mortar joints, leaving the stones unharmed. The wall flexes as a system of individual units instead of shattering as a single mass. The mortar is a network of built-in shock absorbers. Secret number 3. The composite core. When you look at a medieval castle wall, what you see is deceptive. The smooth exterior stones suggest solid construction all the way through, but slice through one of these walls, and you discover something surprising. They are not solid at all. Medieval walls were built in 3 layers. The outer faces used carefully cut ashlar stone, expensive, precisely shaped blocks that presented an imposing facade. But between these faces, rubble, irregular chunks of stone bound together with lime mortar, creating what engineers today would call a composite structure. This was not cutting corners, it was brilliant engineering. The rubble core served multiple purposes. It provided excellent drainage, as water could weep through the irregular gaps. It absorbed movement and settlement without cracking. It created multiple fracture planes. If stress built up in one area, the wall would redistribute that force through the rubble rather than creating a catastrophic single crack. Modern concrete walls are monolithic, one solid piece, which means when they fail completely. Medieval walls were designed to flex, shift, and survive. Section 4. The self-healing discovery. Flexibility and breathability are remarkable enough, but the true secret of these ancient materials is something that sounds like science fiction. They could heal themselves. How is this possible? The answer is chemistry, a brilliant, intuitive chemistry that modern science is only now beginning to fully understand, thanks to groundbreaking research from institutions like the Massachusetts Institute of Technology. The Roman connection. The breakthrough in understanding came from studying ancient Roman concrete, the predecessor to medieval lime mortar. For a long time, researchers were puzzled by small white chunks called lime clasts found in the mortar. They were often dismissed as signs of poor mixing. But a team of researchers at MIT suspected something more. It seemed unlikely that the Romans would consistently make the same mistake in their most enduring structures. What they discovered overturned centuries of assumptions. The evidence points to a process called hot mixing. Instead of using pre-slaked lime putty, Roman builders often mixed highly reactive quicklime directly with dry volcanic ash. When water was added at the end, the mixture would heat up intensely, sometimes over 200 degrees Celsius or 392 Fahrenheit. This process not only created unique chemical compounds, but it also left behind small, brittle, and still highly reactive pockets of lime within the hardened mortar. These were the lime clasts. They were not a mistake, they were an engineered repair mechanism. Now imagine a crack forming in the structure. Rainwater, the enemy of modern concrete, seeps in. As it touches one of those dormant lime clasts, the reactive lime dissolves into a calcium-rich solution. This solution flows into the crack. As the water evaporates, the calcium recrystallizes, forming new calcium carbonate. It literally grows new stone inside the crack, sealing it shut. The crack is not just filled, it is chemically rebonded. This discovery has led researchers to re-examine medieval lime mortars, looking for parallels. While the practices were not identical, the underlying principle, the presence of reactive lime, offers a compelling explanation for the longevity of many later structures as well. The very agent of destruction for our modern world, water, was the agent of healing. They did not design a material that would never break. They designed a material that knew how to break, and more importantly, how to fix itself. They designed for resilience, not just for strength. If you find this look into historical ingenuity as fascinating as I do, and you want to see more forgotten technologies brought to light, take a moment to subscribe. It helps us dig deeper into these stories. Section 5. Case Studies in Endurance. This philosophy is written in stone across the world, in structures that are still standing and in use today. Case Study 1. The castles of medieval Europe. Let us go back to castles like Hereford in England. For over 800 years, its walls have endured the damp British climate. Their longevity is a direct testament to every principle we have discussed. Bedrock foundations that never settle, drainage systems that still function, lime mortar joints that have flexed with centuries of temperature changes, breathable mortar that has wickered away centuries of rain, self-healing properties that sealed micro cracks before they became catastrophic. Case Study 2. The earthen hearts of the Great Wall. In the East, a similar philosophy was realized with an even simpler material, earth. For long sections of the Great Wall of China and the foundations of the Forbidden City, builders used rammed earth. This involves compacting local soil in layers inside a frame until it becomes as hard as stone. Like lime mortar, rammed earth breathes, naturally regulating humidity. The foundations of the Forbidden City, built in the 15th century, have supported its immense weight for over 600 years. While many sections of the Great Wall have inevitably eroded over centuries and required stabilization, the sheer endurance of the original material is a testament to the technique. Case Study 3. The unseen genius of the dry stone wall. Perhaps the most profound examples are the dry stone walls that cross the landscapes of places like Ireland and the Yorkshire Dales. A farmer's wall might stand for 500 years with no mortar and no modern foundation. It survives because it is in a conversation with the ground. It flexes, it breathes, and it lets floodwater pass harmlessly through its gaps, relieving pressure that would destroy a solid barrier. It is the epitome of resilience through adaptation. Case Study 4. The flexible frame of the Borgund Stave Church. Our final stop is in Norway, at the Borgund Stave Church, built around the year 1200. It is a masterpiece of woodworking that looks almost alive. Its longevity comes from a holistic system of flexibility. The timber frame is a masterclass in joinery, using wooden pegs and complex joints that allow the entire structure to move slightly in high winds. The wooden staves rest on stone footings, isolating the timber from ground moisture. The entire building has survived over 800 harsh Norwegian winters, not by resisting the elements, but by gracefully moving with them. Section 6. Secret number 4. The patience we lost. There is another secret to medieval durability that has nothing to do with materials, and everything to do with time. Medieval construction was seasonal. Builders worked from spring through fall, then stopped, not because of labor disputes or budgets, but because lime mortar demanded it. The mortar needed warm, dry conditions to cure properly. Rain could wash it away before it set. Extreme heat would dry the stones too quickly, preventing proper bonding. So medieval masons built according to nature's calendar, not a construction company's deadline. A single castle wall might take 3 years to complete, with work pausing every winter. The slow curing process of lime mortar meant that only a limited height could be built in 1 day, before needing to wait for the mortar to set, sometimes up to a week. If you carried on building before the mortar was set, the weight of the walls would push the mortar out and there would be very little holding the wall together. Today, we pour concrete in January blizzards using chemical accelerators. We schedule foundation pours based on contractor availability, not optimal conditions. We have gained speed, we have lost patience, and our structures show it. Section 7. Why did we abandon wisdom? This brings us to the most perplexing question. If these methods were so superior in terms of longevity, why did we stop using them? The answer, in a word, is speed. The Industrial Revolution ushered in a new paradigm with a new set of values: mass production, rapid urbanization, and infrastructure on an unprecedented scale. The slow, seasonal, craft-based approach of the medieval mason was not compatible. Lime mortar requires skilled labor and time to cure. Bedrock excavation is expensive. Drainage systems take planning. Portland cement, patented in 1824, was the perfect material for this new age. It could be mass-produced, poured by a less skilled workforce, and it hardened in hours or days, not months. We gained the ability to build cities at a speed that was once unimaginable. In doing so, we created a built environment with an inherent obsolescence, a legacy of infrastructure in a constant state of decay that requires a staggering, unending investment in repair. We did not lose the ancient secrets. We simply prioritized something else, building the future from the past. We began with 2 images, the enduring castle and the crumbling wall. For 2 centuries, we have overwhelmingly chosen the path of the crumbling wall. We are now reckoning with the consequences: failing infrastructure, and the immense environmental burden of our most used material. The solution is not to abandon modern technology and go back to building castles by hand. It is to learn, rediscover, and integrate. The answer to our future problems may lie in this wisdom from our past. And that is already beginning to happen. The research into ancient mortars has sparked a vibrant field of research into smart concretes that can repair their own cracks. While still largely in the realm of research and niche applications, these materials are a direct translation of that ancient principle. Architects and builders are rediscovering lime-based materials, not just for restoration, but for creating new, sustainable modern buildings. The techniques that built these timeless marvels were not a step backward. They are a guide to a more resilient and sustainable future. The great secret is not about rejecting the new. It is about finally showing respect for the timeless wisdom that is built quite literally into the world's most enduring structures. What other ancient technologies do you think hold lessons for our modern world? Share your thoughts in the comments. And if you enjoyed this journey into the past to find solutions for the future, please like this video and subscribe for more.